we look at a couple examples of diagonalizability or diagonalization. So let's see. So for the first one, we revisit an old example. So take T to be the operator on C2, which is given by moving the second entry to the first and killing off the other one. So this is the combination rotation and projection that we saw back in clip 5.A.6. Okay, so here U taken to be the span of the vector 1, 0. This is the eigenspace of with eigenvalue 0, and this we saw in 5A.6 is the only non-trivial invariant subspace. Non-trivial, meaning that the others are the zero space and all of C2. And so then we can see from this that C2 does not factor as a direct sum of two spaces, which are invariant and one-dimensional. And so then by the theorem that we just proved in the previous clip, this is an example of an operator which is not diagonalizable. Okay, so now let's look at an example of an operator which is diagonalizable and how to diagonalize it. So here T is going to be an operator on F3, given by, let's see, so T acts on X, Y, Z by mapping it to 2x plus y, 5y plus 3z, 8z. Okay. So in the standard basis, the matrix for T would look like the upper triangular matrix 2, 1, 0, 5, 3, 8. And since it's upper triangular, we can read off the eigenvalues. And they're 2, 5, and 8. Just reading off the diagonal. And that's from 532. Okay, so now we can figure out how to put this, how to diagonalize this matrix as follows. So if we look at the eigenequations, so Txyz is equal to lambda 1 times xyz. Well, then that gives us equations for each of the entries. So 2x plus y has to equal 2x, and 5y plus 3z has to equal 2y, and 8z has to equal 2z. All right, so from the bottom one then, we can see that z has to equal 0, And from the top one, subtracting 2x from both sides, we get that y is equal to 0. And so then all terms in the middle one disappear, and we get 0 equals 0. So there's no constraint on x. And that tells us that 1, 0, 0 is a lambda 1 eigenvector. Okay. And let's see, so now if we take the same thing, but this time we're looking for an eigenvector for 5, then on the right side we have 5s all the way down. And what does that tell us? So let's see. So again, the last one is going to tell us that z has to equal 0. And then we can cancel that middle part, and we see that, I guess, subtracting 5y from both sides, that 0 equals 0, so that one was useless. And from the top one, what do we have? We get y has to be equal to 3x. Okay. So the second coordinate is 3 times the first coordinate. All right, so then that means that if the first one were 1, for example, then the next one would have to be 3 times that. And then we saw z is equal to 0. Okay, and so now we take the same thing again, and we do it for 8. And so let's see, so the third equation now gives us 0 equals 0. And, oops, let me get rid of that purple line. The second one gives us what? So we have 3z is equal to 3y. So in other words, z is equal to y. And then the first one tells us y is equal to 6x. Okay, so let's see. So then v3 is going to be something where if we take 1 for x, then the second coordinate is going to be 6 times that, and the third coordinate is going to match the second. Okay, so we found 3 eigenvectors here, and so with respect to the basis where v1 is 1, 0, 0, and v2 is 1, 3, 0, and v3 is 1, 6, 6. The matrix for T is going to be the diagonal matrix 2, 5, 8.